Welcome to Trigonometry video 2. In this video we're going to look at some of the applications of right-angled trigonometry. So we'll apply the laws of trigonometry in some common right-angle contexts. We'll consider bearings as one of the contexts, and we'll consider angles of elevation and depression. So let's start with bearings. Bearings you'll need to know a basic understanding of. So first of all, if you are navigating, or you're using a compass, or you're using a situation where positions are located based on bearings, you'll need to know this concept here, the idea of a bearing. So we have our north, as you can see indicated here, and we have our south on the opposite side of north, and then of course we have east and west. Now you'll notice here that north is indicated by 0 degrees. So a bearing always measures from north, and it always measures from north in a clockwise direction. So the bearing measures from north, and a right angle of course is 90 degrees. So once we get down to east we have 90 degrees. And then once we get down to south, we have 180 degrees. Once we get to west, we have 270. And once we get back to north, we have 360, which starts again back at 0. Just like if you were using a clock, you get to the end of 12 o'clock and you go back to 1. Now you'll notice here that we also have some in-between angles noted. 45 degrees, or 045, is northeast, and 135 is southeast, and so on and so forth. So there are 8 common bearings. But you can also have bearings in between. So some bearings in between include this one here, which would be about 030. Perhaps this one here, which would be about 220 degrees, and so on and so forth. Bearings could also be noted, 220 for example, could be noted as a bearing from south towards west, so always from north or south, and then always towards east or west, and the actual angle here rather than a 220. So this one would be south 40 degrees west. 220 could be written as start at south and then move 40 degrees towards west, and you'll find the same direction. Remember, this is not a location, it's a direction which can help give us a location if we also have a distance. And of course 30 degrees would be written as north 30 degrees east. Now a bearing is always written as 3 figures if it's just written numerically, and you may see bearings sometimes written as 070 degrees true or 070 degrees magnetic. Now in this context we'll almost always use true, and if you go on to do any navigation from actual maps you'll find that magnetic becomes a very important thing. But true is the bearing to our map based north or our map based south, etc. So you can use that one. So that's all the information we need to have on bearings, and I'm going to go through a quick example. Now I've chosen a reasonably difficult example, but I want to get the point across that once you've drawn the diagram, bearing questions really aren't that hard. You just need to be able to draw the diagram. So I'm going to start down here, and I've made this decision because I know the example. So you should always start with the example and have a think about where on your page you want to start writing down or drawing your diagram. But of course it is just a rough sketch, so if it goes wrong, you just start again. So a plane flies on a bearing of 325 degrees for 80 kilometers. So that's step 1. So I start here and I draw 325 degrees. You'll notice that my line's not really straight and my bearing probably isn't that accurate, but that doesn't really matter for this type of question. So this is 325 degrees, which of course implies that since west is 270 degrees, this is 55 degrees, which may or may not be helpful later on. Now, I'm at a second point here, which I might call point B, given that I'll call the starting point point A. And from point B, the bearing is 55 degrees for 60 kilometers. So a bearing of 55 degrees is 55 degrees from north, and so that is there. And this is, of course, 60 kilometers, and this bearing is 55 degrees here. So now I've travelled along that bearing, and I've ended up at this point here, which I'll call C. My diagram is still pretty rough, and I've got a lot of things drawn on it, so sometimes having multiple coloured pens helps here. Now it asks me how far is his original position, from his original position is the plane, and on what bearing. So let's change colours very quickly. We want to know on what bearing is this blue line from the original position. So original position is A, final position is C, and we also want to know what distance is this. So first of all, what I want you to recognise here is that I've actually flown on a bearing of 325 degrees, which leaves an angle here of 35, which means this is 35, and 35 and 55 make a right angle. So this has created a right angle. So whenever you have a bearing question, if it says travelling north and then east, that will naturally create a right angle. And many other bearing questions will also create right angles. If you're travelling on a bearing that isn't north or east, you can calculate different values by looking at the north and east or the south and east components, and they will create right angle triangles as well. So you've got lots of options. Look for the right angle until you've learnt non-right angle trig. So I've got a right angle there, and I can now take this diagram over to here, just draw a little version of it. Here it is here, and it's pretty rough, but that's a right angle, that's 60, that's 80. This is what I want to know to start with, and would you believe it, Pythagoras Theorem works here. So I have 60 squared plus 80 squared equals x squared. So that gives me 3600 plus 6400 equals x squared, and that gives me 10,000 equals x squared, and that of course gives me x equals 100. So it's now 100 kilometers from his starting position. Keep in mind that because this is 80 and this is 60, we're expecting him to be no further than 140 from the starting position, so just keep that in mind as a bit of an estimate. Now we also need to calculate our new bearing. So to do that, I need to calculate this angle here. And I know my diagram is starting to get quite rough now, but if I can calculate that angle and add it to my original 325, you'll note now that I'll have my new bearing. So let's go back into this diagram here. I want that angle, and I'll call it theta. In this case, I know my opposite, I know my adjacent, I need to calculate my theta. So this is a tan question. Tan theta is equal to opposite over adjacent, which is 60 over 80. So theta is equal to tan inverse of 60 over 80, and therefore theta is equal to 36.87 degrees. And so the bearing is equal to 325 plus that new angle, 36.87 degrees, which is equal to 361.87 degrees. But you'll notice that once you get to 360, we restart. So this is 001.87 degrees. So this example holds many things that you might see. It's quite a rich example. Just keep in mind to keep an eye out for Pythagoras Theorem. It may appear at times. Make sure that you're clear with your diagrams and you pull out the important piece of information. Recycle back to zero if you need to. And just expect there to be a pretty rough diagram at the start. And don't be afraid to draw a new diagram to take the information out that you need. So there's some information on bearings. Let's have a look at angles of elevation and depression. And actually these are a little bit easier. So here's a really simple diagram. And this, of course, is a person, and they're standing there and they're looking out towards something. Now, if they're looking at an object that is above them, then this angle here, which we may call theta again, is considered an angle of elevation because they're looking up, so it's an elevated position. And if they're looking at an object that is below them, then this angle here, which we'll also call theta, just for naming's sake, is called an angle of depression. Depression is a downwards angle, so you're looking down. Now, in most diagrams, you'll have something that looks more like this. You'll have an object, let's call it A, and an object here, call it B. And we'll have dots to represent them, and I'll draw my best possible straight line between them, which kind of missed. Okay, now, in this case, if I change pen colours, you'll notice that if I draw my nice horizontal line here, and my nice horizontal line there, if A is looking at B, this is an angle of depression theta. And if B is looking at A, this is an angle of elevation, theta. And I've deliberately chosen theta in this case because obviously that horizontal line is perpendicular to this horizontal line, giving us alternate angles in the angles in parallel lines topic you've done in the past. And therefore our angle of depression is equal to our angle of elevation. And that's going to be really common in these types of questions. When you have two position holders, two objects looking at each other, or a person looking at an object, the angle of depression will equal the angle of elevation. That can be really helpful. Okay, so I'm going to rub this out now and do this example very quickly. The angle of elevation of a ship from an observer on a cliff is 16 degrees. So here's the observer on a cliff, and here's the cliff, and here is my take on a ship. Okay, and this person is looking down at that ship. And so the angle of depression, so this should be depression, is 16 degrees. And the angle of elevation to the person is 16 degrees. So depression and elevation can be interchanged, but because we said from the of the ship from an observer, it's an angle of depression. So my mistake there. Now if we just cut this dotted line across here, we're told this is 420 meters, and we're asked to calculate the height of the cliff. So we'll call that x. Now I could redraw my diagram here just by putting in a triangle with the important information, including a right angle. But I don't think I even need to do this because this question is reasonably trivial. So now I've got a triangle here where 16 is my angle, because I can move that in using angles in parallel lines, and these are my parallel lines. And I have an adjacent side and I have an opposite side. And you'll see here that the tan ratios come back up again, and this will actually happen quite frequently. Tan 16 is equal to x over 420. So x, of course, is equal to 420 times tan 16, which is equal to 120.433 meters. And that kind of makes sense. You have to be very careful here, though. As you start moving into your senior years of maths, you have to start thinking about assumptions you make. So the first assumption you might make is that the cliff height doesn't include the person's height. And that's a little bit of an issue. Not only that, but down here we haven't included this other height here. So this is the ship height, we'll call S. So we've got to be very careful of that. And we have other situations such as, is this really a right angle? Does the cliff make a right angle of the ground? Is this person actually standing on the edge of the cliff, or are they standing some distance away from the edge? Let's hope they are for safety reasons. So there are other little things that could change the diagram in the context. But all we can do is make assumptions and work the best we can with the information that we have. So there we have it. Two examples of context within trigonometry: bearings and angles of elevation and depression. I hope that's really helped. I look forward to seeing you in the next video.